Hello everyone, welcome to another lecture as part of our ME 6151 Computational Heat and Fluid Flow course. So in the last lecture we looked at three problems from Padankar's book, right, from chapter 6. We looked at the 6.4, 6.5 and 6.7. These three problems, we formulated them, kind of set up the simple algorithm loop. So in today's lecture we're going to see the corresponding programs for these problems and kind of run and obtain the answers. Okay, so the first problem we will tackle today is the problem number 6.4, that is the flow through a porous one-dimensional flow through a porous material. Essentially this is governed by the equation C mod UU plus dpdx equals 0, right? And we were given the pressure points which are 1, 2, 3 and the velocity points which are B and C, right? And the continuity equation was given as d by dx of u equals 0. Delta x, that is x2 minus x1 or x3 minus x2, was given as 2. And we were also given the constants, the porosity coefficients, right? CB, CC as 0.25, 0.2. And the cross-sectional areas A, B, AC are given as 5 and 4. And the pressure boundary condition is given at the points 1 and 3, that is as 238, right? And we were given an initial guess, that is UB star UC star equals 15 and P2 star equals 120, right? And we have to find what is the converged value for the velocities UB and UC and also the pressure P2, right? That's what we have to find. So the corresponding code, the program that I have is in Fortran. All the programs that I have that I'm going to show you today are in Fortran. So I do not have the C counterparts of these, but if you want, you can easily write them by looking at the code this code that I will share with you. So if you want, you can write a C counterpart of it, or you can even use the Fortran programs to kind of play with them and see how they are written and whether it will work for different values or not, and then kind of learn from it. Okay, so essentially what we're looking at this code for simple porous. That is problem 6.4. So we have so essentially this is the declaration part. So essentially we are declaring these variables, that is the cross-section areas A, B, A, C, and the porosity C, B, C, C, and the pressures P1, P2, P3. Delta X is basically your X2 minus X1 and so on, and your tolerance. And A, B, A, C here with little a, these kind of correspond to the coefficients, right? In terms of the AB is the coefficient for the UB, right, whenever we write, and then UB, UC are the velocities at B and C locations. UB prime, UC prime are the corrections for velocities for UB, UC, and P2 prime is the correction for pressure at the location 2. Then we have the under relaxation, that is alpha U, alpha P, the coefficients, and then we also have something known as residual, which is both for U as well as for continuity, okay, for the U momentum equation and for the continuity equation. And then we have this B corresponds to the B term on your in your continuity equation, right? Okay, and then we kind of make use of a couple of integers I and I max. Okay, so what is given to us? The initial guess was given as UB equals 15, UC equals 15, and pressure equals 120, right? That's what was given, essentially UB, UC equals 15 and pressure equals 120. So we initialize to that. We have another set here which we will try later, okay, and anything in exclamations here is a comment, okay, so you don't have to worry about that. Then the given parameters are the porosity. CBCC is 0.25 and 0.2, that is basically given here, and the cross-sectional areas are 5 and 4, that is basically AB is 5, AC is 4, and pressures, the Dirichlet boundary condition for pressure, that is P1 is 200 and P3 is 38, okay, so that is basically taken here, and the delta X is equal to 2, that is your X2 minus X1 or X3 minus X2 equals 2, okay. So these are all the data that is already given in the problem, so this data is given. Next, what we do is we kind of set these values, the tolerance value. So what is the smallest value we want to converge this code to, that is 1 into 10 power minus 6. Then the under relaxation values for the pressure, we kind of set it as 0.8. For the velocity, we set it as 0.9, okay. Then we would also need to do some iterations. Here I put the iteration limit as 200, and hopefully we will kind of break out of the loop before we reach the 200 iterations. Okay, that we need to see. If we do not break out of this, then we have to increase this number to something like 500 or 1000. Okay, and then run them. So so here we have a do loop. This is basically similar to your for loop in C. Okay, in C programming language or C++. Fine. So this is similar to a for loop. Essentially, we are going from I equals 1 to I max in steps of 1. Okay, so that's what we have, and then okay, and then we need to calculate what is this coefficients for the momentum equations, right? So you remember the momentum equation was AB UB equals something, right? Where the coefficient AB was CB times mod CB times delta X, right? So if you go down, I think when you discretize the equation, so these are the equations we got, right? Essentially, the coefficient here AB is basically, how much was it? AB was CB mod UB delta X, right? So that's what we have written here. So CB mod UB delta X is your coefficient AB. Similarly, AC is CC mod UC times delta X. Also, these are the coefficients for the velocities at the staggered locations, okay, for UB and UC. Now, we will not worry about this at the moment. So this is basically the residual. I'll come back to this in a little while. So before we do that, so let us not worry about this part here. So let us look at the solution of the momentum equation. So how do we solve for the momentum equation? Momentum equation is basically you have AB UB equals P1 minus P2. So you calculate UB as P1 minus P2 by AB, right? But of course this doesn't look like that because these are under relaxed equations. Okay, so we have to look for the under relaxed equations that we have written towards the end of the formulation. So that is basically this one. Okay, so we are talking about AB by alpha U UB star equals P1 star minus P2 star plus 1 minus alpha by alpha times AB UB star. So if you were to calculate UB star, then you take this entire thing and then multiply that with alpha U by AB, right? That's going to give you what is UB star for a guess value of pressure and velocity. Okay, so that means if you look at here, so what we have is UB star equals, you have P1 minus P2, same as what we had here, plus we have 1 minus alpha by alpha times AB UB star, that is this candidates 1 minus alpha by alpha U times AB UB star. Okay, so this is AB UB. Now this entire thing of from here to here, right, has to be multiplied with alpha U by AB because this is coming from the left hand side, right? So essentially you multiply with alpha U, divide by AB on the right hand side to get UB star. That's what we have. Essentially we multiply with alpha U, divide by AB. Okay, similarly we write the equation for cell C, that is P2 minus P3 plus 1 minus alpha by alpha times AC UC star, and the entire thing has to be multiplied with alpha U and divide by AC. Okay, so UC equals P2 minus P3. These are the guess values. So we don't have this star notation here because we know that eventually the star is basically what we have is there as the current iterate value, and that is what will be used here. Okay, so we have P2 minus P3 and then plus we have UC times AC times UC into 1 minus alpha by alpha, and this entire thing will be now multiplied with alpha U by AC to get what is UC value. Okay, so this is the solution of momentum equations, right? So once we obtain this thing, we got new values for UB star and UC star. Okay, all right, then let us calculate what is the value of the continuity equation. So the continuity equation is nothing but AB UB minus AC UC. Okay, so let us also not worry about this residual at the moment, and we know that somehow we will kind of exit this loop if the sum of the residuals is less than the tolerance we have specified. Okay, then we say that the solution is converged. Now we will come back to what is this residual, why we are using this as a check. I will come back to that in a little while. Okay. Okay, then once you have the star values for UB and UC, then you essentially go down and solve the pressure prime equation, right? What was the pressure correction equation? The pressure correction equation was P2 prime equals UB star AB minus UC star AC. So that is P2 prime equals AB UB minus AC UC divided by AB by AB plus AC by AC. Okay, so this is AB by AB plus AC by AC. So that's what we have. So we are solving for pressure correction equation. Because we have only one cell, we essentially don't have to solve for a system. Rather, whatever we have would be fine, right? Essentially, whatever essentially we can just write it as an explicit equation, right? We don't have to solve for a system here. But once we know the pressure correction, then we can correct the velocities using whatever we know, right? So what is the relation between pressure correction and velocity correction? Once you know P2 prime, your UB prime would be minus P2 prime by AB. That is written here. This is minus P2 prime by AB. That is UB prime, and UC prime equals P2 prime by AC, right? This is basically your P2 prime by AC. Okay, then UB equals UB star plus UB prime. So here, by the time I come here, UB star and UB are the same, right? So here what I'm using is, this is UB star. When you add it to UB prime, the new value you would get, I'm again storing it in UB. Okay, so UC gets overwritten. So UC star plus UC prime would give me UC, right? Then P2 equals P2 plus alpha P times P2 prime. Okay, so this is the pressure correction equation, and these are the velocity corrections and pressure correction. Okay, fine. So far so good. Then what do we have? Then we have to check. So basically we have done now one iteration. After one iteration, we need to check whether we satisfy continuity or not. What is the continuity equation that we have? Continuity equation is basically, if you go back to the problem, where is the continuity equation? Continuity equation is this one. This is basically ACUC minus ABUB, right? That is basically your ABUB minus ACUC. So if this is satisfied by the new velocities, that is UB and UC that we just calculated here, then that means we got a continuity satisfying flow field. Okay, so that is the idea. Okay, then we kind of print off the values after every iteration. So I is our iteration count, and UB and UC are the velocities, P2 is the pressure. So essentially the problem asked us to calculate all these three values. Then we print something known as the U residual, that is basically the residual coming from the momentum equation, and B is nothing but is the amount by which the flow field satisfies the continuity equation or not. Okay, so that's what we are printing after every iteration. Now let us get back to the U residual and C residual. Okay, so this is nothing but, the U residual is nothing but, if we define something as residual, if you have an equation, let's say Ax equal to B, then the amount by which Ax is not equal to B is known as residual. So if you take all the terms to one side, that means the residual for Ax equal to B would be B minus Ax. So B minus Ax, if it is not equal to 0, that means the x that you got is not satisfying the solution. So that means we have to still improve the x such that B minus Ax equal to is equal to 0. Okay, so that is what is residual, which will be used to see whether the system is satisfying, the solution is satisfying the system or not. Okay, so that means U residual is nothing but the entire equation that you have taken to one particular side. So that means we have ABUB, ABUB star by alpha U. This is basically your left hand side. So we are taking everything to the left hand side. So we have on the right hand side essentially P1 minus P2 plus this is all the under relaxation part. So this entire thing, right, from here to here is the entire momentum equation, which is basically taken to the left hand side. And similarly we are looking at momentum, what is the residual for the other cell. So this is the residual for cell B and this is the residual for cell C. Okay, so we are taking an absolute value of these residuals because we don't want the residual of this to be subtracted by this one. Okay, so we want to see how much is the amount by which this is not satisfied and how much is the amount by which the C cell values are not satisfied. Then we calculate these two. Okay, that is the sum. So U residual gives you the residual for cells B and C. Then we are also updating U residual by its absolute value of the central coefficient. That means AP, UP, AP, right? That is UB, AB by alpha U. So we are kind of normalizing this. This is only kind of a normalization so that like a small quantity that is coming up from these terms would not be overseen. Okay, so as a result, we are just taking the first two terms, essentially the left hand side values, and we are trying to normalize whatever u residual we have computed here, such that even if this comes out to be small, it is with respect to what is computed here, and we would know that the value that you got here is not really small compared to this. Okay, such that we still have to kind of converge. This is basically to take care of this is to take care of the numerical errors or the round off errors, right? So we don't want very small values to be seen as, okay, this is 0 or something. Okay, so this is basically, but by the time u residual goes to, let's say, less than the tolerance, that means we are satisfying the momentum equation. That means the calculated ub and uc now satisfy the momentum equations up to the tolerance. Okay, that's what it tells us, right? So that means if u residual comes out to be 0 or the tolerance value, that means the ub uc that we have calculated now satisfy the momentum equation, right? That's what it is. Okay. Okay. All right. Okay, and you also realize that before, when I do this thing, I have already used the AB as the updated values. Okay, so you may have a question here in terms of, well, we talked about the discrete momentum equation and the momentum equation. So we are talking about the discrete momentum equation in this context, but I have just updated the AB values here. Okay, that means what I use here in this equation is the latest value. So this is the nonlinear value, whatever we have, right? The nonlinear value would be computed here because this is the same UB that is used to check for this. Okay, so that means it will satisfy the same nonlinear equation as such. Okay, so we have just plug in these values. All right, now let us also look at the continuity residual. So we want to see whether the continuity value, that is ABUB minus ACUC, whether this is 0 or not. Okay, again we are kind of taking average of ABUB and ACUC and multiplying with half. Essentially this is to take care of the relative value of ABUB minus ACUC, right? This is basically the normalization here is to take care of small values that may come, which may really look small, but they're actually not small in comparison to what is the each of the flow rates. Okay, for that we are doing this thing. Otherwise you can even check with the ABUB minus ACUC. Okay, fine. Essentially these two, the continuity residual and the momentum residual, this is basically what tells us that if these two together are less than the tolerance that we have specified, which was some 1e minus 6 or something, right, which was 1e minus 6 here. So that means if both of them are less than the tolerance, then then that means we have kind of converged to a particular solution. Okay, and then we are going to print what is the value of UB, UC and pressure at the cell, and we are also going to print the B. B is nothing but the value of the continuity equation. Okay, so that's what we're going to do. All right, so that is as far as the program is concerned. Now let us look at running this program. This is simple porous. So I have these programs here. So I use Fortran simple porous.f90, and then I would run it. Okay, it kind of took 55 iterations. So the columns here are, the first column is iteration, the second one is UB, this is U velocity, UC is the third column, then pressure is the fourth column, then we have the U residual and C residual. C residual is 0. So one thing you note is that for every iteration you see that the C residual, that is the continuity equation, that is the B term, is always 0 or less than the tolerance, right? It's 0, 0, 1e minus 6, 0. That means our simple algorithm is running driving these UB-UC fields through continuity satisfying fields. So at every location that is 0, right? It is always 0. And finally the solution is converged to UB of 12. So velocity at B cell is 12 and velocity at C cell is 15 and the pressure is 128. Okay. All right, so that's what we have. And and what about the momentum equation? So if you look at the momentum residual, initially this is somewhat large value, that is large in a sense, this is 0.18. and you can see that it continuously decreases. So as it converges down, as the u and v and p get u, b and u, c and p get updated, it kind of starts decreasing, and the momentum residual comes down to 1e minus 6. Okay, so but the momentum equation eventually satisfies at this condition, but you can see that the continuity equation is always satisfied by the velocity fields that we got. Okay, and you can also see that the initial guess that we have given is kind of comes down from 15 and 12 or something, and then it kind of comes down to these values, right? So what was the initial guess again? Initial guess given was 15, 15 and 120. So initially it kind of little bit oscillates here between 11, 12, and then it kind of eventually reaches a value of 12. And UC was given a value of 15. That starts off with, from 15 it comes down to 14, 13.8, then 16, and then it kind of oscillates. And the pressure was given as 120, so it starts with 120 and eventually it reaches a value of 128. Okay, so these are the final values for UB, UC and the pressure. Okay, now let us not use what is given by the problem, that is in the book, that is basically 15, 15 and 120. Let us use these new values, that is basically UB is 50, UC is 100, pressure is 1000. Okay, so remember that we have converged in 55 iterations. So we are going to rerun this problem. So this is G Fortran, simple porous, and then run it. Okay, boom. So it kind of converges in just 61 iterations, and it converges the same values, that is 12, 15 and 128. Did it start with what we have given? Yes, it does. It kind of starts, but then you can see that very immediately it kind of comes down to, the velocities come down to 8, 9 and 11 or something, right? And the pressure is very high. This is basically, the pressure correction has come down from 1000 to 345 in like one step, right? And then you can again see that the momentum residual comes down and the continuity is always satisfied and so on. Okay, so that is the as far as the first problem is concerned. Okay, so all right, so let us see, let us now look at the next problem. All right, that is basically the simple porous is done. So what is the second problem? The second problem was the nozzle problem, right? So in the nozzle problem, what we have is basically there is a nozzle that is given and whose continuity and the momentum equations are given. So the continuity equation is d by dx of rho ua equals 0, and the momentum equation is d by dx of rho ua u equals minus a dp dx, right? So essentially that is what is given, and we have discretized this equation, and density is given as 1 everywhere. AA equals AB equals 3 and 1 respectively, and the pressure boundary conditions given, that is 28 and 0, right? And we formulated this, and the initial guess is also given. Okay, so let us see what is the second problem looks like. Simple nozzle. So again we have, these are the definitions, declaration of the variables, that is we have AA, AB, these are the cross-sectional areas, and then in P1 and P3 are the pressures, and then UA, UB are the velocities, right? P2 is the pressure. Essentially we have to calculate what are these values. Okay, and then FA are the flow rates, FA and FB, DA, DB are the coefficients that we get in the prime equations. Okay, similarly we have P2 prime, UA prime and UB prime, these are the velocity and the pressure corrections, and then we have alpha U and alpha P. Okay, all right. So if you see the given boundary conditions are P1 equals 28, P3 equals 0, right? These are already given. So P1 equals 28, P3 equals 0, that is already given, and the geometry is given as cross-sectional areas as 3 and 1, right? This is 3 and this is 1. AA is 3, AB is 1, and the initial guess is given as 5/3 for UA. UB equals 5, so you can take this as 5, okay, and P2 is 25, okay, so this is 25, okay. All right, that is the initial guess for pressure. Okay, the tolerance value is 1e minus 6, again I set it to 1e minus 6 for equations to kind of converge. Then we have alpha P equals 0.8, alpha U equals 0.8, these are basically your under relaxation parameters. Okay, and then again I said these are the iteration max is maximum number of iterations before which we hope to come out of the loop. So this is the loop. So do iteration equals 1 to it max. So we calculate the momentum coefficients. Okay, so the momentum coefficients are basically we have if you go back to the problem, what are the coefficients for momentum? Basically your F2, that is nothing but your FA, right? So okay, for the cell A we have FA and FB, right? So we look at what is FA. FA is your is basically UA times AA, right? Velocity times area, and then we have rho equals 1. Similarly, FB is UBAB, so that is the coefficients here. Then dA, which we get here, this we defined as dA, that is AA by FA. So we calculate, we assign dA equals AA by FA, and dB equals AB by FB, right? So we have those two values as well, and then we use the this is again the residuals. So basically taking the entire momentum equation to one side, this is what we have. Okay, we'll come back to this little later. So what is the momentum equation? Momentum equation is we have to look for the under relaxed equation that we have written. That is basically this value, right? That is your UA star equals AA times P1 star minus P2 star. That is AA times P1 star minus P2 star plus this is basically your under relaxation component, that is 1 minus alpha by alpha times FA UA, and then this entire thing has to be, entire equation has to be multiplied with alpha U times FA, multiply with alpha U divided by FA to get what is UA star. Okay, so that's how you get the UA star, and UB star is also similar. UB star has basically FA UA, that is your FA UA here, right here. Then the second term is AB times P2 minus P3, so that is your AB times P2 minus P3 plus this thing is again coming from the under relaxation, and what we have is multiply this with this entire thing with alpha U by divided by FB to get value of UB star. Okay, so that is UB equals FA UA plus AB times P2 minus P3 plus the under relaxation component, and then we have multiplication with alpha U times FB. Okay, all right. Okay, so just got in here. Okay, so this is your UB, right? Then again the continuity equation. What was the continuity equation? Continuity equation was FB minus FA, right? That means rho equals 1. So this is UBAB minus UAAA. Right, so if your continuity residual would be UAAA minus UBAB, again I'm dividing with whatever is the continuity value, average value, such that this becomes kind of normalized. Okay, similarly now we can understand how this residual is calculated. This is the absolute value for cell A. Oops. Okay, so this is basically the absolute value for cell A, right? So this is FA UA by alpha U. This is the left hand side equation, left hand side part of the equation, and this is the right hand side brought to the left hand side, right? So essentially we have this is for cell A, and we take the absolute value. Similarly we take the other value, that is for the B cell we have FPUB by alpha U minus FAUA, all these things. Basically this is your for cell B. Okay, and again we use we normalize with the central coefficient, that is FAUA by alpha U and FPUB by alpha U, okay, to basically get to normalize this value. Okay, so that's what we're doing. So that means basically this is to normalize the residual value such that it's not going to be very small or very large. Okay, so that is the residual for velocity. So that means if we go back to the algorithm, we started off with calculating the coefficients, then we computed all the momentum equations, then we have to solve for the pressure correction equation. So P2 prime is basically coming from our equation. What was P2 prime? P2 prime was, okay, this guy, right? This is P2 prime equals U star AA minus UB star AB upon DAAA plus DBAB. Okay, so that's what we have in the program. This is P2 prime equals UAAA minus UBAB divided by DAAA plus DBAB. Okay, so that's what we have. Again, we have only one cell, so we don't have to solve for a system. We just plug in what is the value of UA star and UB star and calculate what is P2 prime. All right. Okay. Then once you have the pressure correction value, then you can use pressure correction to correct the velocities, right? So what is the formula for correcting the velocity corrections? Velocity corrections are basically UA prime equals minus dAP2 prime. So that is UA prime equals minus dAP2 prime and UB prime equals plus dBP2 prime, right? That's what we have from here. UB prime equals plus dBP2 prime. So we correct the velocities. Then we can update the velocity UA as UA star plus UA prime and UB as UB star plus UB prime, and the pressure as P2 equals P2 plus alpha P times P2 prime. Okay. Again, we check for convergence. So this is basically whether continuity is satisfied or not. So we look for UA star AA minus UB star AB. This is the value of our continuity equation, right? So with whatever corrected value, so this should satisfy continuity at each and every iteration. Okay, then we print out the B value, that is the continuity value, UA, U2. Let us print out this at the end. Okay, so that means we print out what is UA, UB, and pressure and B. Okay, now if you want, you can also print out what is the C residual, right? So the C residual can also be printed. Okay, so that is the overall algorithm, and then we hope to exit this before the iterations finish through this condition, right? So essentially this is the condition. This is basically tells you that if your residual, some of the residuals is less than the tolerance, then we say okay, we have reached the converged solution and the solution is blah blah blah, that is UA, UB and P2, and then we exit. Okay, so but we have to make sure that we don't run out of the iterations as such. Okay, let us also print what is the iteration count here. So that is I, right? Okay, so we should know that we have not reached more than 100. Okay, let us see if we can run this program. So this is simple nozzle. So G Fortran simple nozzle. Some problem here. Has no implicit type. Okay, so this is, there is no I here. This is basically iteration. Okay, all right. Okay, successfully compiled. Then let us run it. This is ./a.out. Okay, very good. So our program converged in 21 iterations, and you can see this is the value of the velocity and at UA, and this is the value of the velocity at UB. So we converged to 2 and 6, and this is the value of pressure. This is 24 is the value of the pressure, and again you can see that the continuity residuals are always 0 or somewhere small value, whereas the momentum residuals, right, that is the U residual. Oh, this should be U residual. Okay. Okay, let me put it again. Okay, so whereas you can see that the U residuals are always coming down, right? Momentum residual is always coming down, whereas the continuity B equation is always equal to 0. Okay, fine. So we can of course again play with these values, the initial guess values, and see whether the program runs or not. Okay, I leave that for you to do. Okay, so that's about the second problem, that is the flow through a nozzle. Okay, all right, now let us look at the third problem that we formulated in the last class, that is basically in these both problems we have nonlinearity, right? In the first problem, in the porosity case, we have nonlinearity in the source term. In the second case, we have nonlinearity through the convection term, right? So that's why we had to do so many iterations, like some 20 iterations or so. Fine. Now let us move on to the third problem. Third problem was flow through a residential pipe network, right? So essentially we have Q is given as C times delta P, where C is the hydraulic conductance, delta P is the pressure drop over the length of the pipe, and what we were given is, we were given this pipe network with the flow rates and the pressure stored at the 1, 2, 3, 4 all the way to 7, and the velocity stored at A, B all the way to F, right? And we were also given some of these pressures, that is P1 is given as 275, P2 is given as 270, P4 as 0, P5 as 40, and so on, and QF as 40. Okay, all right. So, and also of course the values of all the hydraulic conductances are given, CA to CF, And we were asked to calculate what is the pressure at this P3 and P6, and what is the flow rate through QA, QB, all the way to QE. Okay, so we have to calculate what are all the flow rates. We have formulated the problem using finite volume method, and we said these are the momentum equations, these are the corrections, pressure corrections in terms of the flow corrections. Then we wrote the continuity equation or the mass conservation equation, and we said that the continuity equation will give you one equation in terms of P3 prime and P6 prime, and another equation at junction 6 as another equation in terms of P3 prime and P6 prime, with the right hand side as known values. Okay. Now we have two equations and two unknowns, right? P3 prime and P6 prime. Alright, let us look at the corresponding code. So the corresponding code is a simple pipe network. Okay, so page up. Okay, so again, this is the main program. So these are all the variables that we define: P1 to P6, the pressures; QA to QF, the flow rates; CA to CF, the hydraulic conductance values, right? And then A1, B1, D1, A2, B2, D2 are basically the coefficients that are written. These are basically these are to solve the we had two equations and two unknowns, right? So to solve the pressure correction, okay, pressure correction equation, right? So these are the coefficients, we will see them later. And then of course these are the P3 prime and P6 prime are the pressure correction values at 3 and 6 locations. Okay, fine. Then what was the initial what was the given values? Given values for P1, P2 are given as 275 and 270. So if you look at the values, P1 is 275, P2 is 270, P4 is 0, right? P4 is 0, P5 is 40, and then QF is 20, right? QF is 20. Then CA to CE to CF, all these values I have written out here. CA, CB all the way to CF. CF is 0.2. Okay, so these are the hydraulic conductance values. Now initial guess for P3 and P6 probably may not be given in the problem, so I have taken it as 100 and 100. Okay, of course you can now see if you want to have a different value as the initial guess. Okay, now okay, here I have only I'll let me put like 2 iterations. Okay, but you can put more iterations, but they are not required. We will see why we don't need so many iterations in this particular problem. Okay, so if we look at the equations, what we had was, okay, so the first step is solve the momentum equations. Momentum equations are QA equals CA times P1 minus P3. So that's what we have. This is QA equals CA times P1 minus P3, and similarly QB equals CB times P3 minus P2. That is the other equation. Similarly QC equals CC times P4 minus P3. That's what we have here. QC is CC times P4 minus P3, and so QD and QE. Okay, so with the initial guess values for pressure or using the given values for pressure, we calculate what is the flow rates. Okay, then what we do is basically we got these flow rates, then we have to solve the pressure correction equation. Okay, in order to do the pressure correction equation, we realized that we had 2 equations and 2 unknowns. Okay, so what we do is we basically write out the coefficients. So I am writing these coefficients as basically A1, B1 and D1, and some A2, B2 and D2, right? So that I can solve 2 equations and 2 unknowns. So A1 is basically your CA plus CB plus CC plus CD with all minus. So that's what I have here, right? A1 is a minus of CA plus CC plus CB plus CD. Similarly, B1 is your CD, okay? And D1 is your right hand side, that is QB star, QD star minus QA star minus QC star. Okay, so these values are given, these values are now taken from here. Then for the second equation, we have this coefficient, we are writing it as A2. So A2 is CD, B2 is minus CD minus CE, and D2 is QF minus QD star minus QE star. Okay, so that is the value. Then of course I have 2 equations, 2 unknowns. I can write what is P3 prime in terms of these coefficients. So I would just eliminate the variables and calculate this as d1 b2 minus basically a proper proportion of these d1 b2 minus d2 b1 by a1 b2 minus a2 b1. That gives me what is p3 prime. Similarly, I can write down what is p6 prime as a2 d1 minus a1 d2 upon a2 b1 minus a1 b2. Okay, so basically we are just solving instead of using Gauss-Seidel, we are just directly solving the two equations here. Okay. All right, so that's what we do. Then once you obtain what is p3 prime and p6 prime, we can just correct them, right? So basically correct p3 equals p3 star plus p3 prime. Similarly, p6 equals p6 star plus p6 prime. Okay, so we have done that. Then what do we do? Then we correct the flow rates, that is qa equals qa star plus qa prime. But we know that what is qa prime? Qa prime is nothing but Ca times this is 0 minus P3 prime. So this is minus Ca times P3 prime. Similarly, we know we can correct what is Qb, Qc, that is Qc minus Cc times P3 prime, because P4 prime is 0, because P4 is given as a pressure boundary condition, and Qd equals Qd star plus Qd prime, that is Cd times P3 prime minus P6 prime. That is this value. Then QE equals QE plus QE star plus QE prime. QE prime is CE times P5 prime is 0. So this is minus CE P6 prime. Okay, so this is minus CE P6 prime. Okay, fine. Then we print the continuity equation. Continuity equation is two equations, one for each cell, junctions 3 and 6. So this is QA plus QC minus QB minus QD, and the second junction at 6 is QD plus QE minus QF. Okay. Then we print the residuals for the momentum equations, right? These are the residuals for the momentum equation. Now, if these were also satisfied together with the continuity equations, that means if you satisfy all of these, that means we have converged our solution. Okay. If that is the case, we print what is the pressures P3 and P6 and the flow rates. These are basically what is asked in the problem to calculate, right? Remember, if you go back to the problem, we were asked to calculate all these pressures and the flow rate. So that is these P3, P6, QA, QB, QC, QD, and QE. Okay. So that is the program. So let us try to run this. This is simple pipe network. So G Fortran simple pipe network. Okay. /data. Okay. So what do we see here? We see that in just one iteration, the everything got converged, right? Because it satisfies continuity after the corrections. This is basically the continuity values. Both are of the order of 1 minus 6, and the momentum residual is also satisfied. So that means everything is satisfied after one iteration, right? And the pressures came out as 280, and the flow rates as 30, minus 14, minus 20, 24, minus 4, right? And although we have done another iteration, this is not required because the values actually do not change, right? These values are the same as these values we get here. This is because only one correction is required, because the problem is linear, right? There is no nonlinearity. As a result, the velocity corrections and pressure corrections that we have satisfy both the continuity and momentum equations exactly after just one iteration. Okay, so that's why without any problems, without any having more iterations, we were able to convert these in just one iteration. Okay, so you can have like 5 iterations, but it doesn't make sense because it will just converge to the same value, right? This all doesn't make sense. Of course, you can have a different value for these, so you can have pressure as 200. Let us see if it converges or not. Yes, it converges to the same value, 280. Okay. Oh, but then 200 is a poor guess because the exact value is 200. So let us say 500. Okay, and then say this as 300 and see if it works. Yes, it works. So it should work because there's nothing wrong. Okay. All right. So that means this is done. Okay. So what I'll do is I'll share these programs with you on Moodle, so you can download them and then run them, kind of learn from them, and then they probably will be useful later on with an assignment or something like that. Okay. All right. then I will stop here. I will talk to you in the next lecture. If you have any questions, send them through email to me. Okay. All right. Thank you.